from this example. So what we are going to do is we are going to solve from there. So uh, so this is the question. Calculate the weight of a cylindrical column of water with a height 40 meters and radius 1 meter. That's the first question, right? So then here we're just going to use what we discussed last week, which is what we discussed uh, density, pressure, and weight. So what we are basically just going to be doing today is seeing how we can apply all these principles in able to answer this question. And like I always say, don't memorize, so let's understand this question. So here we are being asked to say, calculate the weight of the cylindrical volume of water with height, which is h 40 meters, and radius 1 meter. So what can you calculate from there? You see, the first thing that you want to do is, of course, you want to know how to calculate the volume of a cylinder. So again, this is something about this because you're going to come across a lot of what can I say, a lot of shapes. So it's very very important that you know how to calculate the volume of the what, the volume of a cylinder, the volume of, so that you know how to apply those. Sometimes they may give you the formula, sometimes they may not. So you always want to be on the safe side. Huh? So there, how are we going to find the weight? How we're going to find the weight is this. Okay, so let's do it step by step so that people don't forget the question. So then, what we are looking at is this. So we've been given. So we've been given. So we've been given that block. Of course, it's in water. So it's in water. Then there is that H there. Then there is yeah. So we're just going to take it one step at a time. So the question is asking us to what? To find what the weight of this particular uh, c- cylindrical column of water. So in short, they're asking us to say this thing that I've shaded, right? What is the weight of this thing? Okay, so they've given us the height to say the height, that's the h I've indicated there, is 40 meters, and the radius, so radius there is what, is 1 meters, sorry, 1 meter. Now we know that from this information we can be able to calculate the what, the volume. Okay, we can be able to calculate the volume. So what's the volume of the cylinder? So volume of the cylinder is pi r squared h, because pi r squared, that's the area, isn't it? That's the area of yeah, so that's the area. Then when you multiply by the height, then you are now getting the what, the cylinder, isn't it? So once you, what you do now from there is you want to calculate the volume. And maybe just to give an overview of how we are going to solve this, is here is the catch. You are going to use, you're going to use the volume to calculate the mass using density. Then you're going to from the mass you can find the what, the weight. Okay, so the volume is, so pi r, so r, so that's 1 meter. Then the height is 40 meters, 40.0 meters, huh? So there you're going to have 126 meter cubed. Huh? This is volume we are talking about. So now with this, remember, so now we can calculate what? We can calculate the mass. Mass is equals to, sorry, density rather. Density is equals to mass over volume. So then, now you may be wondering what volume are we going to use? So this cylinder is what? This cylinder is occupied with water. It's a column of water. So meaning you can look at it to say the density of this cylinder. It's a cylinder of water. That's the thing. It's a cylindrical column of water, right? So the density you're going to use is for what? Is for water, which we discussed yesterday. Which we what? Which we discussed yesterday. Oh, sorry, last week I meant to say. So that's the density of water. Then the volume, that's what we've calculated, isn't it? So that's what we've what? So that's something that uh so that's what we've calculated. So can we calculate the mass? Definitely. So what do we do? We cross multiply. So we are going to making mass the subject of the formula means density times what? Times volume. So we are going to say the mass is going to be the density. What's the density of water? So that's something you have to know. 1000 kg per what? Per meter cubed, and then 126 126 meter cubed. So what you're doing, you are going to do, you cancel that, and you are going to have a mass of what? 1.26 times 10 to power 5 kg. So yeah, you've gotten the mass. Now remember, our original question was asking us to find the what? Our original question was asking us find find the weight. So now what can we do? Weight is what? Weight is mass times gravity. Okay? So where is our mass? Our mass we've calculated there. So I'm sure you may have seen from this question that it's all about just understanding the equations and then making use of them. So that's about it. Then from here, then you're going to get your what? You're going to get your weight. So it all came from the understanding that we could calculate the volume. Then since density is always the same, so then we say, hey, the density is always the same. So you can use it to calculate the mass. Then from there, we could calculate our weight. So that's the first part. So for the second part, let me use blue so that we don't mix the two. Then our second question is calculate the force exerted by air on a disk of radius 1 meter at the water surface. Okay, so what you are looking at in this question is, so remember, we are looking at something like this, right? So now they are saying exerted on a disk of radius. So the water surface is here, right? So the water surface is what? The water surface is here. Then there is a disk which has got a radius of what? A radius of 1 meter. So now, what do we know about this? So first of all, we are trying to find the what? We are trying to find the force which is exerted by water. In short, we know that what's going to be acting on this. Remember, we said pressure acts what? Perpendicular. It acts directly on the thing, right? Or if you want, you may say the force rather. The force is going to be exerted on the surface perpendicularly, right? So there you have it there. So meaning you have your pressure. Now what pressure is that going to be? That remember this they are saying the force exerted by air. So we know what the atmospheric pressure is because we are talking about air. So if we are talking about air, then we are talking about what? About atmospheric pressure. So what is our atmospheric pressure? So our atmospheric pressure, we know that our atmospheric pressure, so pressure of the atmosphere is what? Is 1.01 times 10 to power 5 pascals, isn't it? So we know that. So now what then we are just trying to figure out is if this is the pressure, then what force will be acting on what? Will be acting on our disk. Now why have they given you the shape of this thing that's being acted on? because it is important in determining the area. So we know that pressure is equals to what? Force over area. So force, making force a subject of the formula, becomes force, pressure times area. So then you are saying uh, this area, how can I rewrite, or what's the area of this cycle? So they're saying what? They're saying a disk. Huh? So it's a disk. So just like a disk. So we know that the area of this is going to be a what? Pi r squared, isn't it? It's going to be pi r squared. So now what then we do is we can then come here and say, so the force that we are looking for is actually the pressure times pi r squared. So simply plugging in the values, atmospheric pressure, okay, there. Then you're going to have pi, which is, you just plug it like that from the calculator. You can type it from a calculator, from a scientific calculator, just like that's how you get the full value. Then, and 1 meter squared, which is the radius. So what you're going to get is, so that was the force that the air, or the atmospheric air, was actually what? Are having on what? On this particular disk. So you see the force really is quite big, as you can see, and the reason for this is because the area is small, like we had discussed yesterday, oh sorry, last week. So that's basically how we would go about this question. So now the third part, let me use a different thing so that we don't mix up the things. So then the third question is, what pressure at a depth of 40 meter supports the water column? What pressure at a depth of 40 meters supports the water column? So here, what you are looking at first is, you want to understand the forces which are acting on the water column. Remember from our question, the water column is going to be here. So that's our water column, right? And we know that of course the height of this is what? Is 40. Okay, so 40 meters, isn't it? Now you have to ask yourself and say, what forces are acting on this water column? What forces are acting on this water column? So that you treat this water column as a, okay, so let's draw a free body diagram. So we're just going to draw it as if as just that. Then we're going to look at the forces which are acting. So remember, we already figured out that there is the force that's coming from the atmosphere. The one that we're just from calculating. That's the force from the atmosphere. That's the force from the atmosphere, isn't it? Then what other thing are we going to have? Then we're also going to have the weight. Okay? So we're going to also have the weight. So we're going to have the what? The weight of this particular uh, water column. Then what other force? And this is a force that really we've not really talked about much, but we'll talk about it in the subsequent parts. It's the, you may have heard of buoyance, isn't it? So what basically buoyance talks about is where, have you wondered how uh, someone that uses a wheelchair can be able to stand up in water? I'm sure you may have seen things like that, right? Like how someone that is not able to walk but can almost quite like stand up in water. How does that happen? It happens because of the principle of buoyance. Buoyance simply entails that there is going to be an upward force. Okay, so there's going to be an upward force, and this upward force is being caused by the pressure of water and must equal the weight plus the downward force of air pressure. So remember, this block is not reaching down. Why isn't it reaching down? Even though there is the atmospheric force and the weight of the water, it's because there is a what? There is an upward force. And because this block is in equilibrium, it's not what? It's not moving either up or down. So what does it tell you about the sum of these forces? It simply tells you that the sum of these forces is what? Is zero. That's why this block remains where it is. So then we just have to get those forces, and then we can be able to find our answer. So before we can proceed, are there any questions? Okay, so that's about it. So now let's now write those forces. So the atmospheric, so we are going to put their direction. So that's negative because it's downward for the atmospheric force. Then you've got the weight is also going to be negative. Then this one, the upward force, right? You can call it buoyance or an upward force for now, since we've not yet talked about buoyance. So you're going to have zero, the sum, isn't it? Then what you okay, so let's just put what uh since we're trying to find for the upward force, so what we're going to do is bring everything else to the right. So that, right? So then what do we do? We calculated the atmospheric force. That's what we were just from calculating. That was 3.17 times 10 to power 5 newtons. So that's the thing with this question. So it means that if you missed it there, it means that even this part you get it wrong. So then we calculated the weight of this water column. You remember we calculated it a short while ago, and that's it, right? So we have that. So when we add that, we are going to get what? We are going to get 1.55 times 10 to power 6 newtons, isn't it? So that's the upward force. So this is the force that was actually balancing the atmospheric force as well as the what? As well as the weight of or the weight of the water column. Now our question is not done, and that's why it's very very important to always check your question and not just leave it here. The question is asking for what pressure at a depth of 40. So we know that the depth of 40 is here, right? So we're looking at the pressure at that point. Okay, so now we are looking for pressure. So this force that we found, we want to find the pressure for it. So we know pressure is what? Pressure is going to be force over area. So we know, uh, okay, so we know that, remember, we are talking about what? The water column. So area, so first the force, which force are we using? The upward force, isn't it? Because we are just trying to find, we found the force, but we want to find what pressure really is there. So the upward force, then the area, which is pi r squared. So we just plug in the values. And then, so that's pi. Then the radius is 1 meter, isn't it? So that's going to be 4.93 times 10 to power 5 pi. Yeah. So that's it. So you see, really, with these questions, it's all about just understanding what's happening. and being able to relate with the formulae which are there. And once you understand, and because you see, for us to answer this particular question here, we needed to use the what? The free body diagram. So you see, free body diagram is very, very important. You may remember when we were looking at the Newton's laws, I talked about how just a free body diagram can determine whether you get the question right or wrong. Because if your free body diagram is wrong, there is pretty much nothing you can do. Because it means that your arrows will be wrong, your vectors will be wrong. So it tends to affect so many things, right? So please let's ensure that we practice free body diagrams. Otherwise, that's about it. Huh? So that's for that question. So now we can now begin to talk about the deformation of what? Of solids. So in our introductory session last week, we talked about the states of matter and how solids tend to be what? How solids tend to have a definite shape and a definite volume. However, it's possible to change both of these things, both of these, both the shape and the volume of a solid. Okay, and this is just by applying external forces. And what happens is that for these substances, so long as the forces which you've used are not too large, the substance can be able to go back to its normal arrangement. But if the forces which have been used are too large, what then happens is that this particular solid can actually lose its what? Can actually lose its integrity. Can lose its integrity. But however, if the forces which have been used are not really large to cause a permanent deformation, then after the external forces have been reduced, the objects can what? Can return to normal shape and volume. Okay. This is called elastic behavior. Okay, so the elastic properties of solids are discussed in terms of stress and strain. Now, these are two things which people usually get mixed up. So, stress for is pressure causing a deformation, or in other words, it's force per unit area causing a deformation, which is the same because force per unit area is pressure, right? So force per unit area causing a deformation, that's the stress. Then the strain is the deformation that is caused. Okay, so if somebody is punched in the face, that pressure that has been used, that force that has been used, that's the stress. And then how bad the face is deformed, that's the strain. The other way you can remember strain is, think of it as pulling a metal. So whenever you're trying to pull a metal, what's going to happen? Or when you're trying to pull, maybe let's say a cable or maybe something elastic, you say, oh, these things look strained. Huh? Okay, so you are there you are referring to the what? You are referring to the amount of deformation. Why am I stressing on this point? Because many people make mistakes on these, and we'll look at an example and I'll then remind you to say this is why I was stressing on this point. So, for sufficiently small stresses, stress is proportional to strain. Why are they saying for sufficiently small stresses? Because, yes, okay, so stress is what causes deformation. Then strain is the amount of deformation. Okay, yeah, so stress is the force per unit area, or it's the pressure that causes deformation. Then the amount of deformation is the strain. So for sufficiently small stresses, stress is proportional to strain. Now, why are they bringing it out to say for sufficiently small stresses? Okay, it's because, like I said, once the stress is too much and the substance is permanently deformed, then the proportionality is what is lost. You may remember things like we did when we were looking at spring potential energy, where we talked about the Hooke's law, and we said so long as the spring is not deformed, Hooke's law is going to stand. Okay, but then if the spring is deformed, Hooke's law is not going to stand, because that particular substance, that particular material is going to be deranged, and it cannot be able to return to its initial position, right? So now that's what we have. So stress is equals to elastic modulus times strain. So the elastic modulus, you can pretty much think of it as your spring constant. Huh? Why is it a spring constant? Because it's what can tell you as to how easy or how difficult it is to what? How easy or how difficult it is for something to what? For something to be to be strained. Okay? So the elastic modulus is very, very important. So now there are different moduli. So the first one that we are going to start with is the Young's modulus. So the Young's modulus really is important when we come to talk about things such as elasticity in length. So what the Young's modulus is going to be looking at is going to be looking at the aspect of the elasticity in terms of length. So what this basically means is you are looking at what? You are looking at the aspect of saying, really, if I, okay, so you are looking at the aspect of saying, if I apply enough stress on this material and it changes its length, okay, and then you want to find out that constant. Remember, if for a spring, we would call it what? Spring constant. But if we are looking at a deformation or the elasticity in length, then what you're going to have, instead of spring constants, you're going to say that's your Young's modulus. So I want to iterate this to say we define the tensile stress to be the ratio of the magnitude of the external force to the cross-sectional area. So you see, stress is a pressure, because remember, force over area is what? Is pressure, isn't it? So that's why the SI unit of stress is Newton per square meter, which is the Pascal, the same unit of pressure. Then strain, the tensile strain. So before we can talk about tensile and compression, do we know the difference between tension and compression? So compression is when we use the example of a banana. If you get a banana, right, a ripe banana, if you put one hand on either, or if you put one hand on either side of the banana, then begin to pull your hands apart, you are testing the tensile strength of that banana. But then if you get the banana and just using one hand or even both hands, but you press on the middle of the banana and begin to squeeze the banana, that is compression. Okay, so let's just get that one straight. Huh? And the reason why I'm stressing is because we are going to look at certain values where they tend to differ for compression and for tension. Like you see the ultimate strength of materials. So you see there is the tensile strength and compressive strength. So you should be able to get that information from your question, or else you're going to use a wrong value, and even though everything that you may have been doing may be correct, you get the question wrong. So that's about it. So the tensile strain is the ratio of the change in length. So remember, Young's modulus talks about elasticity in length. Huh? So they like this as an MCQ, huh? Multiple choice question. That's if they still give you the MCQs. So tensile strain is the ratio of the change in the length to the original length, and is therefore a dimensionless quantity. If you divide length over length, the meters are cancelling, isn't it? If the meters are cancelling, it means that you don't have a unit. So I hope we get the difference, because stress or tensile strength has got a unit, which is the Pascal or Newton per square meter, whereas strain doesn't have a unit, doesn't have units. So what we arrive at now is what is that equation 9.5, and we see that that y there is what we call the constant of proportionality, or we call it the Young's modulus. Okay, so that's an important thing. So you can look at this diagram which I've zoomed in on your screens. So what this is showing is, remember when I was talking about spring constant. So you see, so long as you are in this area, I'm sure, okay. So long as you are in this area, you see that so long as you don't cross that elastic limit, you see that the proportionality of stress and strain is maintained, isn't it? But once you cross this point, the this proportionality is what is deformed. Okay, so once that proportionality is deformed, it means that the material, it's at a point which is critical. Hmm? It's at a point which is critical. So that's about it, right? So now, if a material subjected to a stress beyond this elastic limit, okay, doesn't, okay, so a material subjected to a stress beyond the elastic limit ordinarily doesn't return to its normal length when the external force is removed. So now it's like the deformity is what is becoming more or less permanent. Huh? Then, as the stress is increased further, it then surpasses the ultimate strength. So you cross the elastic limit, the proportionality is broken, and this substance cannot return to its original length. Its elasticity is what is damaged. Then, as the stress is increased, it then surpasses the what? The ultimate strength. The ultimate strength is the greatest stress the substance can withstand without breaking. So, meaning you've tried to pull the banana. Remember the example that I gave about the banana. So, you are pulling the banana, pulling your hands apart, and then that ultimate strength is that greatest strength which the banana can withstand without ripping apart, without breaking, isn't it? And then once it reaches just beyond the ultimate strength, then you're going to have the breaking point. That's where maybe the banana will just cut in half. Okay? But for brittle materials, that's where you can find maybe yeah, something gets damaged like that. Okay? But for metals such as gold, copper, when you are pulling them like that, what actually happens with them is that the metal is going to get thin and stretched at a lower stress level before breaking. So what this simply means is, I'm going to give an example of a plastic. If you are pulling a plastic, right, to begin the initial pull, like you want to destroy a plastic by pulling it will be very hard at first, but it reaches a point where the plastic becomes thin so much that to pull it further you're not having to, or rather you don't have to use a lot of energy. Okay, so that's what they are saying happens to these metals as well, right? So you see that for a plastic it will be easy. You just pulling a bit until it breaks. So that's about it. So that's about Young's modulus. So I just want to bring these moduli in perspective. Then after we've done that, I think then we can look at examples. That way we'll be able to even differentiate these moduli. So Young's modulus is elasticity of length. So meaning the object has got a change in its length. Then you've got the shear modulus. So we know something about shear. Shear is when you've got, let's look at uh, this diagram here, the one that I'm now projecting. So you see the shear stress displaces the top surface of the block to the right relative to the bottom. So let's look at this book that this person is having, right? Have you ever tried to hold the bottom surface of a book and then put your hand on the top and then try to slide your hand where across the surface? Your book will be doing as though it's becoming bent, isn't it? It will be becoming bent in some way. So you see, it will be as though it's becoming like a parallelogram, right? So if it was something that was maybe like a square or something, you will notice that there will be a change in that. If it was something rectangular, so much that if it was something that was rectangular, it will now become a what? It will now become some sort of a parallelogram. So that's something that's important. So now this kind of force, and one thing that's important about this this thing that we are talking about, or this shear modulus, is that the force is parallel to the what? To the surface. Okay, so the force is parallel, and you can see here to say the forces which are of course we know that the bottom forces, that's just friction, right? But the top force, you see the top force for this one, it's parallel to the what? To the surface, or to the surface area of what? Of the object in question. And that's what shear stress is all about. So they're just talking about the book which I've already talked about. Now, what's shear stress? So shear stress is basically the ratio of the magnitude of the parallel force. Here's the thing, parallel force. Parallel force is the key thing. Okay? Is the key thing in this. Okay? So the parallel force to the surface, or rather to the area A of the face being sheared, right? So meaning that this force has to be parallel so much that the surface is not compressed but it's sheared. Okay, I'm sure you may remember, those things you used to do for the transformations where the shape will change from a rectangle to a parallelogram, things like that, right? Okay, so that's about the shear stress. So you see, it's just ratio of the parallel force to the area. Again, that's giving you what? Pressure, because that's the same as force over area, which is pressure. Then the shear strain. So remember, strain is the what? Is the amount of the deformity. So you say the change in x. So what is x? X is the horizontal distance the sheared face moves. So what is the x? Look at this. You look at this diagram, right? Originally, okay, so I'm going to draw something here. So originally, this block was starting from here. So this block was starting from here. But then what happened due to this force? This block, instead of starting from here, it was then moved by what? By this distance which they are showing here. So it was moved by that distance. So now this distance now, the one that they've calculated is the one which we are now having as what? As the change in x. So meaning it's been moved. Originally it's as though if something was like that, 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 let's just draw this. So if you had something like this, okay, so if this was the normal, right? And then after the shear happens, I'm just going to draw this part. Then this part changes and it becomes displaced. So now this displacement that has happened, okay, you see that the original part was actually at this point, but then there is this added distance which has now come up, and it is this displacement that we are now calling the what, that we are designating rather as the change in x. Okay, so that's the ratio. So it's the ratio to of the change in x to where, to, or rather, and the height of the object. So the height of the object is simply the height that this object has. Okay, so once you've gotten, so you know your stress, your shear stress is force over area, then your shear strain is the change in x over h, then that s there is the what, is the shear modulus. So something to mention about the Young's modulus is that something that has got a large Young's modulus would be difficult to what? Would be difficult to elongate. Then something that has got a large shear modulus, so something with a large Young's modulus would be difficult to stretch. Then something which has got a large shear modulus would be difficult to bend. Okay, so that's pretty much about. So take note of these formulae because these are the ones that we'll be using when we start examples. Yeah, we're just remaining with to discuss the bulk modulus, then we can do the examples. So what bulk modulus really looked at is this. Okay, so let's look at this. So when you look at this, what's happening? So with bulk modulus, the shape is not changing. The shape is maintained, but what changes is the volume. Okay, or in other words, the size. Okay, but we know size and volume are the same. So this is a situation where if you've got an object which is you get an object, you put it down in a fluid, there will be forces which will be acting on that object from the fluid, isn't it? And so that's about it. So otherwise, for the bulk modulus, the forces will be acting so uniformly, so much that they don't cause a shear what, a shear, or a shear, or a Young's modulus. They don't cause elasticity in length, or shear elasticity. But what is going to, or the change in shape, but what is going to cause is the change in volume. Okay, so what then is going to happen? So the volume stress is defined as the change in the magnitude of the applied force to the surface area, which is the same as the what? Which is the same as the change in the pressure. And you see here is quite interesting because for the others we are just saying the ratio, but for this one we are actually saying it's the ratio of the change. Why are we saying the change? Because there has to be a change in the pressures for you to have a deformity. Like there has to be an initial pressure and a final pressure that then causes what? The changes that we are seeing. Okay? So that's an important thing to take note of. Then you've got the volume strain. So what you are looking about, what you are really focusing on about the volume strain is so the volume strain. So you remember, strain is the amount of deformity, right? So the volume of strain is equal to the change in volume divided by the original volume. So here I'm just trying to find how much change has happened or has occurred in this substance, or rather in this object of interest. Now you see that if you've got a material which has got a large bulk modulus, then it's hard to compress it. Now you may have seen that there is a negative sign that has been put in this equation, and the main reason why it's been put there is to ensure that B is always negative. Oh, sorry, is to ensure that B, the bulk modulus, is always positive, because there's no way you can have a bulk modulus that's negative. And why is this important? Because if there is an increase in pressure, it means that the final is greater than the initial. So meaning the change in P will be positive, isn't it? But if the positive, but if the change in pressure is positive, it means that there is a compression of the object, meaning the change in volume is going to be a negative value, because it's going to mean that the final volume is less than the initial volume. So you're going to have negative. So to ensure that when we are trying to find the the bulk modulus, we don't have a negative value. So that's why they've put that negative value there. So don't memorize, just understand it the way I've put it. You won't have problems. Huh? So then there are certain times where instead of putting up the the bulk modulus, there is something which is used called compressibility. So what compressibility simply is reciprocal of the bulk modulus. In short, it's 1 over the bulk modulus. That's what reciprocal is, isn't it? So sometimes why I'm stressing this is sometimes they'll give you a question where they want you to find the change in the volume, but they don't give you the bulk modulus. Rather, they give you the compressibility. And then someone says they didn't give me the bulk modulus. It means that you've not appreciated the the relationship between the bulk modulus and compressibility. So please always remember, compressibility is simply 1 over the bulk modulus. Huh? Okay. Then remember that there is no Young's modulus or shear modulus for liquids, because if remember, Young's modulus is a tension, is a tensile, is a pulling force. So if you pull a liquid, the liquid will just follow through, no deformation. Then we talk about the shear modulus. If you are trying to apply a parallel force on the liquid won't argue or have a shear. No, it will just simply flow in the direction of the force. However, both solids and liquids have bulk modulus or bulk moduli. Why? Because you can compress a liquid. Okay? Sometimes you may have tried where you put water in a bottle. I think we used to do this with those bottles, not these bottles for Apple Max, but those bottles for Yes Drink. Huh? Yeah, like those bottles where the lid is a little bit loose. So you would have to put water in the bottle, put the lid on top, and then squeeze the bottle. And eventually, what would happen is, because we are compressing the water, we are going to cause the what? We are going to cause that compression causes because of the we are trying to change the volume of the water. Okay, we're trying to reduce the volume of the water, and remember to reduce the volume of the water by compressing, the pressure increases. So we are practically increasing the pressure in that bottle, and that's why the lid or the cap of the bottle would what would fly over, right? So that was just something to remind us and to just explain further about pretty much what the bulk modulus is about. So now we can now look at an example. So this example is so again, yeah, so example 9.2. So when you look at a question, okay, let's look at this. A vertical steel beam in a building supports a load of 60,000 newtons. A. If the length of the beam is 4 meters and its cross-sectional area uh, is 8 times 10 to power negative 3 meters squared, find the distance the beam is compressed along its length. So the key things just from what I've read is a vertical steel beam. Why is the steel important? Because the steel lets you know which substance which substance you're going to be focusing on when it comes to checking whether it's going to be a Young's modulus or it's going to be a what. Okay, so the material very important. Then you also want to check for find the distance the beam is compressed along its length. What is that telling you? Is that an elasticity in length? Is it an elasticity in in shape, or is it rather an elasticity in volume? So you answering that is important because that determines whether you're going to use the Young's modulus, the shear modulus, or the bulk modulus. But here we know they are talking about length, so it's going to be the Young's modulus. So we end here for today. So we've looked at all the moduli. So tomorrow will just basically be answering the questions and then pretty much, yeah, see if we can wrap up this topic over the weekend. So otherwise, that's pretty much about it. So before we can go to the next course, are there any questions?